Okay, so I received a few emails regarding potential flows and a few questions that you had. So I'm going to go over the topic. I'll solve a few problems. Probably I'm going to solve 3 problems. Now I will start with a small description, and then we'll go into how to synthesize the problem, or what are the steps to the solution, what kind of questions to expect, and how to solve those problems. So first, the description that we have 4 types of canonical flows. We have the uniform flow, we have the source and the sink, we have the free vortex, and we also have something that's called the doublet, which is basically a source and the sink superimposed at a given position. Now, the potential flows, they're actually given by either by velocity potential or by stream function. Now, all of these flows have both a velocity potential and also a stream function. All of the above functions or relations, they do satisfy the Laplace equation, which is very important. By knowing this, we can superimpose the functions to construct any type of flow or shapes, just as we did in the lab, where we were able to create the half Rankine body. We're able to see what's the effect of a source with a uniform flow and whatnot. Now, the steps for this to solve any of these problems, they are very mechanical, and basically most of the time you're going to be using the same thing. First, you will construct your stream or potential functions. Then next, you will find your u and v, or vr and v theta if you're working in a cylindrical coordinate. And finally, you will answer the question. Usually the question will tell you find me the stagnation points or find the pressure and velocity, and we can definitely use Bernoulli because the velocity potential is there, which means that the flow is irrotational. So moving forward, a small definition here, or side note actually, the uniform flow, which is given as we saw by phi equals x cosine alpha, y sine alpha, and xi by u cosine y cosine alpha minus x sine alpha. It's important to note that the alpha is actually the angle that the uniform flow u makes with the x-axis. So alpha is the angle that we make with the x-axis. So when we have a flow which is parallel to the x-axis, I can say that my alpha is 0. By saying so, my phi will equal to ux and my xi will equal to uy. Basically what I did here, I just replaced alpha 0 in the equation above for the phi and the xi. Now, in simple geometry, my x is r cosine theta and my y is r sine theta. So I have finally my phi equals ur cosine theta and my xi is equal to ur sine theta. You can choose to work in any coordinate system that you want. You can choose to construct your flow either by the stream function relations or with the potential flow. That's up to you, okay? And if you try both ways, you will definitely get to the same answer. So let's start with one problem here. Okay, so the question says a flow field is constructed by uniform flow and a free vortex in a counterclockwise rotation at the origin. Determine the pressure variation in this flow field expressed in terms of u, r, and the pressure p naught, which is far away from the origin. Okay, so this is a question typically that shows up. Now, how would we solve this problem? First, I will go back to the steps and I'm going to follow exactly my steps. So before doing so, I will underline here that I have a uniform flow and a free vortex counterclockwise rotations at the origin, and I need to find the pressure variation using u, the intensity of the circulation, and p naught. Okay, so these two things here, uniform flow and the free vortex, is the things that I will start with. I'm going to go up here and I will go to step 1. Construct my stream function. Construct my actual flow by a combination of stream relations or velocity potential relations. Okay, so for the uniform flow, I have 2 options. I can use the potential flow or I can use the stream function. Okay, and now for the free vortex, I can use the relation of the phi or I can use this relation. Okay, now what I would do, I would avoid anything that has to do with natural log of r. I don't want to deal with this. You can do it if you want to, but myself, I don't want to deal with this. So my choice will be solving this problem using the velocity potentials. Okay, so let's start by step 1. So start step 1. So I have phi is a combination superposition of two functions, phi uniform plus phi of a free vortex. Okay, so I have phi equals, I'm gonna go up here, I have u x cos alpha plus y sine alpha plus, from the tables above, I have r over 2 pi theta. Okay, now I know that my flow is a uniform flow. It's parallel to the x direction. Therefore, I'm going to replace alpha equals 0. So I'm going to end up with u x plus the intensity over 2 pi theta. Okay, now I have this relation. It is very important that you must choose one coordinate system. So I cannot work with x and theta. I'm gonna have to have either to work with x and y or r and theta. So the easiest way to overcome this problem is by using this relation here. Phi is u r cosine theta plus circulation 2 pi theta. Okay, so I reached here my first milestone. Okay, I would box this because I would get partial marks on this part here. Okay, so step number 2, let's go up and check. Find u and v, or vr and v theta. Okay, now obviously I'm working with r and theta, so I'm gonna have to find vr, step 2, and v theta. Those are given relations on your formula sheet. By now we should know this. So we have, for vr is d phi by dr. Okay, so I'm going to integrate this function here, actually differentiate the function with respect to r. So I'm going to end up with u cosine theta. Next, I'm going to use for v theta my other relation. V theta is, it's given, I'm actually looking here in the book. The relation is 1 over r d phi by d theta. So if I differentiate, I'm going to end up having u, r will cancel by r, differentiate cosine theta, I'm going to have minus sine theta, plus if I differentiate the next one, I'm going to have circulation gamma over 2 pi r. Excellent. Okay, so now here I have my second milestone. Okay, now if we do this too, we're 70% done with the problem. Next, the question is asking me to find the pressure. When I say pressure or velocity, I'm going to think Bernoulli. Alright, so Bernoulli between 2 points. One is at the origin and the next point is far away. So Bernoulli's equation has P1 over gamma plus V squared over 2G equals P naught over gamma far away plus V squared over 2G. Okay, and the answer should be in terms of U, gamma for circulation, and P naught. Okay, so I need to find if we say this is far away, so this must be u. That's given here. So I need to find my v. And we know that v squared is vr squared plus v theta squared. Okay, so this gives me that my v squared is u squared cosine squared theta minus u sine theta plus r over 2 pi r. Now this is my second one, so I'm going to have to square this and add a plus sign here. Okay, so we're almost done. Now I need to find the pressure P equals P naught plus 1 over 2 rho u squared minus v squared, which is equal to P naught plus 1 over 2 rho u squared minus, I'm just going to copy u squared plus ur, this is gamma over 2 pi, actually it's only 1 pi, r sine theta minus circulation gamma over 2 pi r squared. Okay, and that's the answer for the question. The problem is solved. Those problems are very simple if you follow the steps of the solution mechanically. Just construct your flow field by superimposing the given canonical flows right away without thinking. Find the two components of the velocity and then answer the question. It's going to be Bernoulli, or find the stagnation point, or it could be some other thing that I'm not aware of yet. So this is the first video. I'm going to try to upload 2 more to help you out. Here.